Hi everyone. This video is about a special form of magnetism, namely diamagnetism. I've chosen the following experiment to show you the effect and its effects. For the experiment you only need 4 neodymium magnets and a piece of graphite. If you position the graphite piece in the middle of the magnet, it will float. The repulsive force between the magnets and the graphite is so great that you can weigh down the graphite plate with cotton swabs. Let's look at the structure of the experiment again in the animation. To explain to you why the graphite floats on the magnet, I'll show you another experiment. For this experiment I cut out the bottom of a tea light so that only an aluminum ring remained. I attached this ring to a tripod rod with 2 threads and a little sticky tape. I also need a permanent magnet. I'll show you briefly that this is a magnet. Hopefully in slow motion you can see that the aluminum ring is repelled by the magnet as long as I move towards the aluminum ring with the magnet. The question is, what happens in the aluminum ring when the magnet approaches? To do this, we switch to the model level. The small dots in the aluminum ring are supposed to represent some free electrons in the aluminum. As soon as I approach the magnet, these electrons move in a circle. This effect is called induction, and it only occurs with electrical conductors. The direction of the induced current is now decisive. As the magnet approaches, the electrons move in such a way that they generate a magnetic field that is opposite to the external magnetic field of the bar magnet. In this case, the south pole of the bar magnet and the south pole of the magnetic field of the aluminum ring, through which the current flows, are opposite. However, since the free electrons do not move without friction in the aluminum, their movement stops as soon as I do not move the bar magnet any closer to the ring. This also causes the magnetic field around the aluminum ring to disappear. But what does this experiment have to do with our graphite? If you take a closer look inside the graphite, you will find electrons there that are bound but not localized. These are so-called pi electrons. An external magnetic field now ensures that these pi electrons form circular currents. The direction is such that the circular currents form a magnetic field that is opposite to the external magnetic field. Important, these are not induced currents, but this form of magnetism is called diamagnetism. So here too, there are 2 poles of the same name, in this case the south pole and the south pole, facing each other. This leads to a magnetic repulsion. However, since the pi electrons can move without friction, their movement does not stop and the magnetic field caused by the circular currents is retained. If you take a closer look at the neodymium magnets, you will see that the following arrangement is present. 2 of the neodymium magnets point with their north pole and 2 with their south pole in the direction of the graphite plate. As a result, 4 areas are created in the graphite plate, because in each area a magnetic field opposite to the underlying magnetic field of the neodymium magnets is generated. The individual areas of the graphite plate therefore experience a resulting force that points into the center of the 4 neodymium magnets. A look at the underside of the graphite plate shows once again that 2 poles of the same name are facing each other and that this is the reason for the floating graphite plate.